Here we'll discuss antiderivatives of functions. So the first question is, what is an antiderivative? We say that capital F of t is an antiderivative of little f of t if capital F prime is equal to little f. Essentially, it is the reverse of the derivative. An antiderivative is what function has this as its derivative. And in general, an antiderivative is not unique. It is possible to have more than one antiderivative. However, if we have more than one, they only differ by a constant. This is our notation for an antiderivative. It's also called an indefinite integral. We say it's indefinite because it doesn't have bounds. And in general, what this looks like is some kind of antiderivative that we're going to be able to find plus a constant, c. Like I said, you do have multiple antiderivatives, however, they only differ by a constant. So we put a plus c to demonstrate that we can add constant values to the end of this and still have an antiderivative. Our first rule says the integral of a constant b dt is bt plus c. As an example, the integral of 5 dt would be equal to 5t plus c. And we can double check the derivative of 5t plus a constant. Well, the derivative of 5t is 5, and the derivative of a constant is 0, so we did get back to where we started. For our next one, as long as our exponent is not equal to -1, the integral of b times t to the n is b over n plus 1 t to the n plus 1 plus c. And this should make sense. When we take a derivative, we subtract 1 from the exponent, so it makes sense that we'd want to add 1 to reverse that. In addition, when we take a derivative, we multiply by the exponent. So to reverse that, we now need to divide by this exponent. A couple of examples using this. Here, we would want to add 1 to the exponent, so 3 plus 1 is 4. And then we divide, and 4 over 4 would be 1. So we just have t to the 4th plus c. For our second example, adding 1, -2 plus 1 is -1. Then we divide the coefficient by -1. -1 divided by 1 is 1, so we just have t to the -1 plus c. A couple more examples. For the first one, we have an exponent of 2. So we want to add 1 to make it 3, and then divide. 6 divided by 3 is 2. So we have 2t cubed plus c. For the next example, adding 1 to the exponent makes it a 5, and then we divide by 5. So we have 7 over 5 t to the 5th plus c. So this shows us how to deal with exponents provided they are not -1. But what if it is -1? The derivative of, or the integral of 1 over t dt is ln of the absolute value of t plus c. So the integral of something like 3 over t dt would be 3 ln t plus c. And it is important to have these absolute values since natural log is not defined for negative numbers. Looking at trig functions, the integral of b cosine at dt would be b over a sine at plus c. And the integral of b sine at dt is -b over a cosine at plus c. The main takeaway here is if we have a number with our variable inside of a sine or a cosine, we need to divide by that number whenever we take an integral. As an example, the integral of 4 cosine 7t dt would be 4 over 7 sine 7t plus c. The last one we'll consider here is an exponential function. b times e to the at dt would be b over a e to the at plus c. Once again, if we have an a or some kind of number with our variable t as the exponent, we're going to divide by that. As an example, the integral of 3 e to the 5t dt would be 3 over 5 e to the 5t plus c.